But the early systems weren't exactly perfect. A phone call signal could start from, say, Paddington Station in West London. Travelling with 2,000 other calls simultaneously down the same fibre, the signal would start to deteriorate. It could get no further than Liverpool Street Station, 5 miles away, before it had to be converted back to an electrical signal, cleaned up and retransmitted. The problem lay in the way the light was behaving inside the fibre. Light that takes a zigzag path down a fibre will obviously take longer to arrive than light that goes straight down the middle. Lasers can produce light of both kinds, and the earlier fibres allowed these modes or variations to follow a choice of tracks inside the fibre. Imagine that this block of motorbikes is a pulse of light. The cones mark the edges of the fibre. When the pulse enters the fibre, some of it is bent and bounces off the walls, while some goes straight ahead. Because the core of the fibre has a greater refractive index than the air outside, the light can't actually escape. The result is that the pulse gets spread out and stretched. Now watch what happens if you try to send in 2 pulses, one closely behind the other. This overlapping is called smearing, and the further you try to send the message, the worse it gets. This is what smearing would do to a television signal. The original fibre was called multi-mode because it permitted all these different modes or patterns of light. The answer was a new mono-mode fibre, a fibre with an incredibly fine core. The previous pathways or modes are no longer permitted. It's down the middle or nothing. The signal stays clear. Now, in theory, it's possible to send those same 2,000 calls from Paddington Station all the way to Victoria Station. That's Victoria Station in Manchester, 150 miles without a repeater. So today's fibres are amazingly efficient.